Welcome everyone. This is the third video in our series about conducted emissions. In this video, we discuss the most commonly used countermeasure against conducted emissions, filtering. First, we explain the basic approach when it comes to filtering and discuss various filter architectures. Based on an example, we show the approach to finding the right filter for a given source and load. We then shift our focus towards the different building blocks used in a typical filter against conducted emissions and merge these components together to form an effective filter. We conclude this video by giving a short summary. So without further ado, let us dive straight into the filtering of conducted emissions. The general idea of filters is straightforward. We want to remove a certain frequency range from our input signal while letting the remaining frequencies pass through the filter unattenuated to its output. Ideal filters cut out everything outside of the desired frequency band, while real filters have a transition from the so-called pass band, where signals are forwarded to the output, to the stop band, where signals are blocked by the filter from reaching the output. We differentiate between analog and digital filters. Analog filters can further be subdivided into active and passive filters. Passive analog filters are built with resistors, capacitors, and inductors. If operational amplifiers are used as well, we call it an active analog filter. Digital filters, in contrast, use logic blocks or signal processing for their realization. This might make the filter non-time continuous or non-amplitude continuous. Some of the most common filter types are low-pass filters, bandpass filters, and high-pass filters. In this video, we focus on the low-pass filters used for blocking the high-frequency conducted emissions from propagating into our power distribution network. When it comes to designing a filter for this application, there are three important architectures, named according to their typical sketch form: the L filter, the pi filter, and the T filter. As depicted, each of these filters only consists of capacitors and inductors, forming a connection between the input or source and the output or load. All of the presented filter structures are low-pass filters. The idea behind these low-pass filters is to create an impedance mismatch for high frequencies, which leads to a minimization of power transfer. By exchanging the inductors and capacitors with the opposing component, each architecture can be transformed into a high-pass filter. However, since we want to protect our power distribution network from high-frequency conducted emissions, we only consider low-pass filters. Also, note that we do not want to use a resistor in the high current path of these filters, as the dissipated power of such resistors in the power path would cause too much heating, resulting in losses. Now let us consider the following example. Consider a system where both the source and load have a low impedance. We want to place an efficient low-pass filter between them to filter out unwanted high-frequency signals. Consequently, since the impedance of the source and load are low, we must place inductors with a high impedance at high frequencies as the closest element towards them. This creates a mismatch in impedance as the source and load impedance are low for high frequencies and the inductors present a high impedance. By placing a capacitor between the two inductors to filter high-frequency signals, we get a T filter. Now that we understand the basic concepts of filtering, let us look at the components used for a typical filter for conducted emissions. A typical inductor for filtering out the common mode emissions is the so-called common mode choke. It consists of one coil for each power line coming from the power distribution network, which are wound around a common core material. It is essential for the common mode choke to have the same direction of winding for the coils, as the magnetic flux caused by differential mode signals will cancel, reducing the effect of the choke for these signals. While the remaining stray inductance is negligible for low-frequency signals, we can still use this inductance for filtering purposes. Contrary, for the common mode currents, the magnetic flux adds up. The magnetic flux induces a current that counteracts the common mode current. Therefore, common mode signals see a large impedance. Consequently, since the flux of the differential mode current cancels out, the core material must be dimensioned to avoid entering saturation solely for the common mode currents. When it comes to capacitors for building a conducted emission filter, there are two important classifications, so-called X and Y capacitors. The X capacitor, also often related to as line-to-line capacitor, is placed between the lines of the power supply. This horizontal connection allows to filter out differential mode disturbances as well as surge peaks and fast transients. There are subclasses labeled with numbers ranging from 3 to 1, with lower numbers meaning higher voltage ratings. Similar, the Y capacitor, also known as line-to-ground capacitor, is placed in a vertical manner between the power lines and protective earth. This is the only exception where the protective earth may be used. It serves as a path to filter out common mode disturbances. Also, the Y capacitor has subclasses ranging from 4 to 1, with lower numbers again being rated for higher voltages. Typically for such X and Y capacitors, foil capacitors are used. However, for example, also ceramic capacitors can be used, and we should always keep the different advantages and disadvantages of each type of capacitor in mind to build the best filter possible. Now, let us use this knowledge about the different filter components to build a filter counteracting the conducted emissions of our DUT. Let us assume a 3-wire system with 2 power lines and a protective earth. After performing measurements of the conducted emissions, we find that the DUT is exceeding the regulatory limits. To reduce the emissions, we first tackle the common mode disturbances by adding a common mode choke between the DUT and the power distribution network. To finish the common mode filter, we must add a low impedance path between the 2 power lines and the ground line. Therefore, 2 Y capacitors are placed between the power lines leading from the DUT towards the choke and the protective earth. In a second step, we want to tackle the differential mode disturbances. To achieve this, we must add an additional X capacitor to the filter. This X capacitor, along with the leakage inductance of the common mode choke, forms an LC low-pass filter for differential mode signals. Optionally, if the necessary space is available, a dedicated differential mode inductance can be added to each power supply line between the Y capacitor and the DUT, forming a 2-stage LC filter. A resistor is placed in parallel to the X capacitor for discharging purposes if the power supply is disconnected. The time constant of this discharge should be in the order of seconds. Note that the presented filter is just one option on how such a filter against conducted emissions can be designed. The placement of the components may vary depending on your design. With that said, let us recap on what we learned in this video. Filters are the most common countermeasure against conducted emissions. We use them to filter out unwanted frequencies between a source and a load. In case of conducted emissions, 3 types of low-pass filters are typically used: L, pi, and T filters. When it comes to filtering common mode disturbances, common mode chokes as well as Y capacitors are used. For differential mode signals, we use X capacitors and the parasitic stray inductance of the common mode choke. If there is additional space available, dedicated inductances against differential mode disturbances may be added.